Previously, I used Monte Carlo and Monte Carlo tree search, and today I will try to use value estimates instead in order to solve the game. So this was the past agent. Let me just run this code. So the game of Nim, just to recap, is you have n match takes. Each turn, player will take 1 to k, and the player will take the last match take loses. So this is the game itself. We can have some sample agents. You can run the game, and you can see like perfect wins all the time. In terms of a tournament, the perfect agent wins like almost all the time unless the random agent does perfect moves. Okay, Monte Carlo will just take the reward and just roll out. So you can see that it takes a while for the Monte Carlo to work, but with the right rollouts, okay, with enough rollouts, like here's 1,000, it can actually do better than the random agent as what we discovered earlier. Okay, so let me just move on. Okay, we don't really need all this. Okay, this for Monte Carlo perfect rollouts, Monte Carlo tree search. Okay, so over here, actually, I would like to change a bit of this code, okay, in order to make it more generic, so that like regardless of whatever node it is, we will still be able to, regardless of whatever game it is, we'll still be able to like sort of know what we'll basically be able to tell this for any game. So let me just edit this code a bit. So instead of like having a valid moves here, okay, I want to make this code more generic. Okay, what I want to do is I want to like have an environment here. Okay, and the environment, what we'll do is we'll use this nim environment to initialize certain things. So nim nk. Yeah, then in this case, we don't really need self.valid moves anymore because we can then invoke self.environment.valid moves, which we can then update this code here. Yeah, so we can do this here and then like, okay, so we also will need something to indicate what the move is. Okay, so over here, the move itself will be basically like what basically is the move that was done, okay, to reach this node. Okay, so that this node will know for sure what move to select. Okay, so this one will be like that. So we will need to give a new parameter called move. Okay, and then this move can be none as well, so that we will know like what move this is. So then we can update here, instead of having this here, we can just put like this best child dot move. Okay, and then when we like implement our best child here, okay, we will need to give it the move itself. So next move will be here. Okay, so whenever we give the child, we will need the next move as well to log it into the child's move over here. So that's what we do. And then like once we initialize the Monte Carlo tree search, we need to give a move, and the first move will be none. IDEX, yeah, I'm actually trying to use, this was the last time I did the stream, and this I used Monte Carlo tree search to try to solve the game of Nim. Okay, but it took a while. Okay, it did not give perfect play. So now I try to use some form of value methods, like using a value for the state. It's something like dynamic programming actually. Reinforcement learning and dynamic programming is very similar. Yeah, it's all about using the value of the next state to update itself. Okay, so I just try to run this class of node again to see whether this works. So I just updated this to make it more environment agnostic, so I can actually create the and change this environment here to change what is required for the search. Yeah, you can just change this environment, okay, with this name like that. So yeah, I think this should do the trick. Okay, let's see whether this works. Oops. Node has no attribute valid moves. Okay, so let's see. Um, Here. So this one needs to be dot environment dot valid moves. Okay, in fact, over here, instead of this, I can do epsilon. So I can define an epsilon here. Or actually, I can just do 1e minus 9 for a very small number. Object of type method has no length. Okay, so the environment.valid moves is a method, so I need to call it. Okay, so there's a slight issue over here because I do need to pop this. Okay, so what I need to do is, yeah, perhaps I'll still need this one. Yeah, yeah, maybe I just revert back to the initial code because I will do one a valid moves list here. So like that, let's revert it. Revert this. Node environment has no environment. Ah, there we go. Length of this. Okay, so actually I didn't change much. I just changed the move over here to make the move explicit instead of implicit. So this move will be the move required to reach this node, and this one will be the remaining moves that you can take to, yeah, correct. Yeah, but actually MCTS doesn't work too well. You need to actually do some form of like AlphaGo or AlphaZero procedure to like keep updating the value estimates in order for it to look better. Because in traditional Monte Carlo tree search, you actually need to search through the entire game tree, and sometimes this need not give very good results, especially if you have a very deep tree. So a way of catching the like value of each state of this node here is very important for games, and that is something that yeah, that is something that needs to be done. Okay, so let me just continue to do this. Remaining nodes that you can take uh, to go to the next child. Yeah, I've been thinking whether yeah, I would like to do the community puzzle and coding game. It's just that this few days been quite busy. But when it's out in the bot section, maybe I'll attempt it. Okay, so let's continue with this. I think this is already done. Let's just see whether this works. It should win against the random agent most of the time. Uh, I think it's okay already because Singapore has found alternate suppliers. Yeah, I myself haven't been affected that much, so I think it's fine. Okay, let me just run these agents to just make sure it's all working. So I think it is working already. This move here is indeed updated correctly. Okay, so this should be model agnostic now. Like in this environment here, you just need to change this environment itself. So yeah, change the environment for different moves. Yeah, so you can do that. Yeah, this already more or less done. Okay, so yeah, I think it's working as expected. Okay, so now let's do what we set out to do in this stream. Okay, this stream using value estimates of a state for planning. Okay, so what we want to do is we want to give each state a value, and the value of each state will be the maximum value you can attain taking a one step taking a one step action from that state. So we will do this, and we will just look through all the states, and in order to get like what basically it's like a dynamic programming is in order to get the value of the next state, we will just look ahead one step and just take the maximum. So basically what we'll do is we start from value of 1, and then we start from the value of the end state, which is at 0, and give it -1 points. Okay, then basically we know which states are bad. Okay, so how we do it based on turn. Should I do the value based on turn? So like we have a value of a state plus a turn, so the turn will give it the value, because then we need to take. Okay, so based on turn, we either take maximum or minimum of the values. Okay, so this will be like that. Okay, so maybe what we'll do is we start with a value list. So maybe value of, so it'll be like something like dynamic programming in some sense. We do have a value, and we initialize the value to be like a dictionary maybe, or we could do it based on like an array. So like numpy dot array, let's see, do it like, okay, let's say I have only 21, so I can do like that. V 0 for num in range 21. Okay, so maybe we have a defined train and then we like do n and k. So basically the n and the k will be like defined based on what we want. So like train the value network based on the inputs n and k. Okay, and in this case the inputs will be n is the total number of matchsticks, and k will be the total moves. Okay, so we start with 0 is, we start with a list of 0, so maybe like v1 and v2. V is 0 for what in range n, and then we also have v2 will be 0 for what in range n. Okay, this will give us the initial values, and then we just loop through like maybe n times. Okay, iterate through, iteratively update the values n times. Okay, so when we run this, we can do an n squared loop, I guess. Yeah, so this is a very inefficient way, but this is how this can be done using like dynamic programming. Okay, when we update this, okay, what we do is we iteratively update. Okay, for I equals 0, I in range n, j in range n. Okay, we will basically loop through, okay, the maximum and minimum values respectively. So firstly, start state is negative for both players. Basically, to reach that state is actually a bad state. So like that, v1 0 equals to -1. v2, actually I don't need this underscore, and just do this. v1 like that, v2 0 will be -1. Okay, and then maybe we can even say the next state will be positive. v1 1 will be 1, because if we can reach this state here, like at the end outcome we can reach this state, we actually win the game. Yeah, we could do this. Start state is negative, and then start state is positive here. Then we just loop through these values here. So yeah, I think what we can do is we can okay, so if let's say we reach this state of 0, actually do we need two values? Because I don't think we really need to differentiate the players, right? I mean, each player will basically not want to achieve a certain state. So this v will be like, if you reach that state, what will be your value? So I think all all will be the same value. Yeah, so maybe we can just do this. Then like if we reach a value 0, okay, as a start state, okay, we will actually be very unhappy about it. And then we basically update this n times, and then for j in this, okay, okay, if, okay, so this j itself, we don't need to start from 0, because 0 and 1 are already fixed. We can start with 2. Okay, 1 you win, 0, okay, you, okay, so 0 is win state and 1 is lose, sorry, 0 is lose state and 1 is win state. So what we do is we update this n times from 2 to n, okay, and then we just basically update the value. Okay, the value will be okay, for move in range k, range 1 comma k plus 1 actually, if j, because j is your starting state, okay, so j minus move greater than 0, okay, then what we'll do is we will basically call this function. Okay, so actually this is dynamic programming. We need to sort of know what is the earlier function. So if j minus move greater than 0, oh, I got it. Yeah, so we will just do the maximum possible move. Yeah, vj will be equals to max of vj and vj minus move, because we need to make sure that this is a valid move. Okay, then we do this, we update, okay, update the value estimate with the highest possible value. Yeah, so that will be what we do. Okay, or actually we should update it with the lowest possible value, right? Because that's no, with the highest possible value, because we want to basically reach there. I'm just afraid that if I do this, what will happen is everything will become one. Yeah, because if we do for both players, it will be like one, right? Mhm. Just what might be max for you, like in this case, our max here will be max of maybe minus b, minus this one. Okay, because this is the other player's move. The other player would want to make it as small as possible for you, so you choose the max of this thing here so as to, now let's just try this. Okay, and then what we do is we just return v. Okay, so let's say we have this v equals to train 21 3. Okay, let's just see what v is. So we can see that v is like minus 1 1 1 1, so all these are winning states. Okay, and then after that, when it comes to this part here, okay, this player would take one of these three here. It actually is a losing state. No, yeah, because all these three are ones, so if I were to do like that, this will be a losing state for this player, because actually if you think from this player's perspective, whatever move you do here will be a loss. Okay, but for this player, whatever move you do here will be a 0 instead. So I guess what I should do is, instead of starting from 0, I should start from like minus 10 or something. Yeah, okay, that makes sense, because if not, 0 will dominate the output. So over here you can see that if you are like v 0 1 2 3 4, yeah, v4, okay, it is a loss, because whatever you do, the other player, okay, will choose the move that will counter you. But if you are over here, like at v5 0 1 2 3 4 5, at v5, you want to go to this move, let the other player go to this move, because this player would lose at this move, right? So you want to go over here. So yeah, you can see that in distinct chains, you already see which states are the winning states and which states are the losing states, just by using this value estimate alone. Okay, of course we could also do like deep queue network for this, where we sample by trajectories, but that's kind of overkill for this game. Okay, I just want to highlight that actually if you are able to get the right value estimates, okay, in this case we just basically choose the maximum good moves based on what your opponent can do, and since it's symmetric, we can use the same value states for both players. Just doing this alone, okay, actually we just need to loop through one time. I realize we don't need to do so many times. We just need to update the values from left to right, from starting state to ending state, and then we can sort of already see that this is going to be optimal. So if I were to change this to like 5 like that, so this actually is similar to the perfect play agent, okay, but is a really uh, efficient perfect play agent. So this game is not very difficult, in all honesty. Yeah, you can see that we have the right values here. Okay, so what we want to do now is we want to define a, okay, a perfect play agent maybe. Yeah. So okay, where's my perfect play agent? My perfect play agent is here. So I want to do the same thing that I did for the Monte Carlo, okay, over here on the value. So if you can get your value of the state perfectly, there's no need to do Monte Carlo because you can just use your value to choose your actions. So let's see how this is done. Okay, so over here, I will do this as value estimate agent or value agent, NK valid moves. So basically, choose the move that returns the highest value. So what we do is like this. If for move in this, okay, if n minus move, okay, or for move in valid moves, that's good enough already. Okay, what we need to do is, okay, we will need to know what is this v over here. So we already given it v, okay, we can just call it from outside the function. So we call this train, and then we straight away can use this. So v, okay, maybe what we do is we'll just do a train nk. I mean, it's not going to incur much cost. Okay, and then what we do is best move equals to none, and then best value equals to minus 10 or something. Okay, v, and then we just take v move, okay, to just check. Okay, v n minus move actually, the next state. So if this is greater than our best value, okay, what we do is our best value will be equals to this, and then our best move will be move, and then what we need to do is just return this move. So we have this, choose the move which gives you the highest value based on one step look ahead search for update of value state. So this is really good because the state transitions are all deterministic. So the state value is definitely accurate. If you start from the smallest value, you move up to the next few values, definitely going to be accurate. Okay, it's only when like the transitions are kind of probabilistic, then maybe you need to run more things. And it's also good because the number of states are kind of bounded, is like quite standard what the bound is. So if you have more complicated states, like maybe you have like more stacks, 5 or 6 stacks or 7 stacks, 8 stacks of matchsticks, then maybe this will get more tricky because your array size will be unbounded, or rather it will be exponentially increasing. If let's say we have like one stack of 21 matchsticks, and you like have 20 stacks of these 21 matchsticks, you will have a 21 to the power of 20 array size. Again, that's where neural networks might come into play to sort of estimate the value of the state, which we can try to implement this a more difficult problem using maybe deep Q learning or deep Q network. NIM can be made more complicated, definitely. But this version of NIM is a simple one. We can actually do this. And then what we can do is, okay, while we have the value agent, we can actually train a tournament to test out how good the value agent is. So let's try it. So random agent, and then we have value agent here. List index out of range. Okay. Okay. Why is it out of range now? V1 is out of range. Okay, that's interesting. The index out of range is here. V1 equals to 1. Oh, okay, okay. Because over here n might be 0. So okay, so we have to do one more step here. Yeah, in fact, maybe I don't even need to specify this v1 equals to 1 because it can already like know for sure based on the update of the previous steps. Okay, so let me just do like, and then I just want to see what the value of v is like that. Okay, so over here, if I were to do -1 like that, uh okay, because I start with 1. Okay, I have to start with range 1 like that. Okay, so this works now. Okay, so I start with 0 and then I just loop through from the value 1 onwards. Okay, in fact I can start with 0 so because then there's no valid move for that. But okay, we can start with 1. Okay, train all this like that. Let's see the random agent and value agent. Oh, it's not exactly returning the best move though. That's weird. Okay, let's just see the game, okay, between the random agent and the value agent, and we see what's wrong with this. So the value agent here is player 2. So over here, is given the value 5. Okay, actually this part he's doing well. 17 takes 3, but here he gives 11. So why though? Why? Okay, so let's have a look. Okay, so what is my V11? It's 1. Okay, so V11 is given a value of 1. That's kind of weird. See again, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so I think what I have to do is instead of like if you want to take a look at this value here, this value needs to be a negative of the earlier values. Like for example, after I go to 0, okay, the result should be, okay, let me think about how to do it. So there should be only one good state and the rest should be the failure states. Like this tree here, they're all failure states. Two, no, two is actually a winning state. So if you can go here and you can get to a state 2, okay, so this state here should be a state 1 should be a losing state. So it's not a state 0 that is a losing state, it's a state 1 that is a losing state because you take the last matchstick is at value 1, not at value 0. So maybe what I need to do is I need to have two losing states, value 0 and value 1. Mm, okay, I think I know what to do. Okay, this part here is from 0 to n. So this 0 actually represents there's only one matchstick left. Yeah, let's just make it clearer. We just do it like that. 0 is a losing state. 1 is also a losing state. Okay, if n greater than 1 or n greater than 0, then we do this. So this one is basically no matchsticks is a losing state. Actually, no matchsticks is a winning state because if you reach a 0, then you win. Okay, you don't want to be the one getting the 1 state. Whenever you get the 1 state, you lose. Okay, so if n greater than 0, I'm just afraid people will just go to the 0 directly. So actually this is also a losing state. Yeah, so no matchsticks is a losing state, and having only one matchsticks is also a losing state. Okay, let's see how this fares. So this will be 0, 1, 2, 3, 4. 2, 3, 4 are actually winning states. Okay, if you get a 2, you can take one matchstick and the other person will be 2, 3, 4 are winning states. This one is a losing state. Okay, let's see how this fares. So player 2 over here is not exactly doing the right moves. Okay, when he gets 17, it's actually doing the right move already. 1, 3, 2. Over here, it gets the wrong move. It should go to 7. It should go to 9 actually. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so actually this -1 parts are what it should strive for rather than this parts here. Should go for here. But 17, what's V17? Okay, so over here it goes for this. So it means what? It means that V18, in 18. Okay, so I think this one should be updated to be the negative of this move here, because this will tell us what is the opponent's move, and then we just need to take the negative of this. Okay, looks like it's working. Let's just try the tournament again. That's funny. Yeah, update this. I mean, it's doing okay until it takes two matchsticks and loses the game. So I guess what I should do is I should make it a winning state for that player. No matchsticks is a winning state. Having one matchstick is a losing state. So yeah, we should update this accordingly. Here's okay, here's okay. Somehow when it reaches here, it gets the wrong value. Like it gets, instead of giving it 9, it gets 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In this case, 9 is a losing state for some reason. So, uh, but if we were to do it like that, oh, because I didn't do the negative sign here. Okay, now it loses all the time. Okay, so it means that actually it was doing fine all the way until the last one. So it means that I need to say no matchsticks is a losing state as well. Okay, now it's playing to lose, I think. The player 2 takes 3 matchsticks. He could have taken one matchstick. 1, 0, 1, 2, 3, 4, 5. Yeah, it needs to go to this value here actually. So actually, as long as my value is a -1, I should take it. Why is it not working though? It should work already. Like it's n minus. So weird. Yeah. Yeah. I thought it would work actually. The value. Yeah. So Monte Carlo tree search is okay. But you know, when I do random and then this is the value agent, it just doesn't work for some reason. You know, if I just change this to like that, will it work? Because I just really need to make sure that if this is -1, then just return this. Yeah, okay, this works. So somehow uh is greater than best value, then best value equals to best move equals to move. Yeah, somehow if I were to do this, I don't get the best. Oh, what a rookie mistake. I return move instead of best move. Okay, so I should return best move and this should work already. So whatever logic is coded here is correct. Then it wins all 10 games. And we can see in the same thing with the tournament. Tournament 10, yeah. You can see that it wins all the games. You can try beating it with the perfect agent, and you can see that it wins all the games as well. So this value agent is already perfect in nature. So you can see that, okay, this one no. So like for example, the perfect agent, even I do like 1201, okay, against the value agent, this, okay, will take a while. Okay, maybe I should have used such a huge number, but you can see that even then the value agent, because in this case this is still a 4n plus 1 number, the value agent works. Okay, so the value agent is winning already just by doing this. I wonder if I make this a one state, whether this will work. It seems to not care about this, because if it can reach the one state, it will go to the one state, it won't go to the zero state. Okay, this state actually, I think, uh, if we hadn't done something like this, actually this should be like, if you have no match stakes, okay, you receive a state with no match stakes, is a winning state actually, because you don't want the AI to like from three choose like this rather than this. You want it to choose one rather than zero. Okay, I think that more or less concludes this. So this is a perfect strategy by just using like dynamic programming to just look through this. Okay, this is only possible in NIM, because NIM, you can have a very well defined progression of states. If you have states that keep recurring like in loops with one another, not a single direction, then you cannot use this method. And perhaps you have to use some form of value estimate methods, and maybe give deep Q networks. I don't know, continuous states, you have to use like actor 2 critic or PPO. Yeah, you cannot do this very nice thing if there's like recurrent loops. Okay, this only works, this dynamic programming method done only works when it's no recurring loops. Okay, uh, okay, so over here, so actually I don't really need this here. No match stakes is a winning state. Having one match stick is a losing state will come as a default. I just put it here. So we start at a state of 0 and give it 1 point. Okay, we won't really want this state, okay? And state of 1, give it -1 points. Okay, based on each state, we choose the move that gives it the least negative value of the next state. Okay, the other player plays to win. Uh, Other player has opposite reward function. Okay, so it's like a mini max. Okay, we do it like that. Start 0 and state of 1. Maximum value you can take from taking a one step action. Yep. So I think that's more or less it. This kind of works, and yeah, I'm pretty happy with the outcome. So to do this as value agent and this as random agent. Okay, so yeah, I will be posting this notebook soon, and yeah, that's the end of the stream today, and I hope you all learned something. So I guess this I'm also trying to experiment around with like all these value methods urban policy methods next time. Yeah, so it does show that the game of NIM can be solved easily using this kind of single one loop as ON time complexity. Okay, but maybe for other games you may not be able to do this, but for NIM you can do this. Okay, and that's it for today, and see you around. Bye.